Hi and welcome to Unit 2 Topic 1 Complex Numbers, and this is video 6. So in this video we're going to look at solving quadratic equations, and this leads really directly towards the Unit 3 work where you'll be solving any polynomial equation that has complex solutions. So let's just recall a couple of things first. A quadratic equation could have 0, 1 or 2 solutions in the real numbers. So you've seen these before, and just to give you a bit of a reminder, over here is a set of axes. And I'll draw, first of all, in pink, a 0 solution quadratic looks like this, does not pass through the x-axis. Here's another 0 solution quadratic. And this time in purple, a 1 solution quadratic will go up and touch the x-axis, that should be touching, or maybe come down from above and just touch the x-axis, but not go over it. And then our last option is this more standard in green, 2 solution quadratic, which has 2 solutions through the x-axis there. So that's what we're dealing with. Now, if it's got 2 solutions, then they're real, and there's no complex solutions. But it turns out that this pink one here, and this pink one here, well, they actually have solutions, but they're complex solutions. So remember here formally that the discriminant, if the discriminant is greater than 0, there's 2 solutions. If it's equal to 0, then there's 1 solution, but it's a double solution called a double root. And if it is less than 0, then the quadratic has 0 solutions in the real plane, but it has has complex solutions available. So for example, if the discriminant is equal to -9, then the square root of the discriminant is equal to the square root of -9, which is 3i. And then we've got a game on our hands because 3i can be included in our solutions, even though that imaginary value gives us an overall complex number. So let's have a look at solving using the quadratic formula. And I think here, for some reason, these should be equal to 0. But we can solve these equations using the quadratic formula. I still haven't written 0 there, to give us a solution. So we'll start with A. And for A, we've got z squared plus 2z plus 10 equals 0, leading to A equals 1, B equals 2, C equals 10. So therefore, x is equal to -b plus or minus the square root b squared minus 4ac all over 2a. And we can solve this, giving us -2 plus or minus the square root of 2 squared minus 4 times 1 times 10 all over 2 times 1. That gives us -2 plus or minus the square root of 2 squared is 4, minus 40 is -36 all over 2, which gives us -2 plus or minus, and this becomes 6 times the square root of -1 all over 2. Now I can split this up. If it's all divided by 2, I've just zoomed in there. I get -1 plus or minus 6i over 2, which gives us -1 plus or minus 3i. So it's a quadratic, it has 2 solutions. One of them is -1 plus 3i, and one of them is -1 minus 3i. And that just came straight from the quadratic formula. Took a while, predominantly because I mucked around, but you could certainly do it quicker. And part B, which is going to be very similar, but we get a slightly different A, B, C value. So I'll jump straight into the quadratic formula. X equals -b, which is -1, plus or minus the square root of b squared, -1 squared, minus 4 times 5, which is A, times 5, which is C, all over 2 times 5. And this becomes 1 plus or minus the square root of 1 minus 4 times 5 is 20 times 5 is 100. 1 minus 100. So this looks less likely to be nice. Over 10. Now I might break it up into real and imaginary now. 1/10 plus or minus, and this is the square root of -99 over 10. Now I can do a little bit of work with this. 1/10 plus or minus, and I can take 9 out as a common factor, so that's something nice. And I can take root 11 out, leaving me with the square root of 9 is 3. I'm left with 11, but I'm going to have that multiplied by the square root of negative 1. So doing that separation, if I bring everything together there, I get negative 99 again, but it does mean I can get the I out as a separate thing. So I get 1 over 10 plus or minus 3 root 11 over 10 I. And that's my final answer, the best I can get. Not as nice as A, but you know what, that's going to happen sometimes. Alternatively, and as you've seen before, we can solve by completing the square. So in example 2, we've got some other alternatives where you can complete the square. So we'll start with A over here. Z squared plus 9 equals 0. Now this one here, the square's already completed because there's no linear term, there's no something z or it's 0z. I can just write this down as z squared equals negative 9, which means that z is equal to the square root of negative 9, which is equal to, and it's plus or minus by the way, plus or minus the square root of 9 times the square root of negative 1 is equal to plus or minus 3i. So 3i or negative 3i. That's A. A is pretty easy. B is a bit trickier. I'll run B underneath. So you might have to go back and recall your work on completing the square for B. But I can write this down as z squared plus 4z plus 4 minus 4 plus 8 equals 0. So this is how I'm completing the square. You'll notice that this is what we already had. This is what we already had. I'll add that little stroke in our z to make it look like a z. But we've got these two new terms, plus 4, minus 4. And it doesn't matter, we've added 4 and minus 4, so we haven't actually changed the equation. But this component here, the first three terms, are a perfect square and can be written as z plus 2 squared plus 4 equals 0. And so there we have it. And now I can solve this equation because I've got that z as a factorised thing. So I get z plus 2 squared equals negative 4. Z plus 2 equals plus or minus the square root of negative 4. So z is equal to negative 2 plus or minus 2i. The square root of negative 4 is 2i. And there's our solution to B. So we can do it by completing the square as well. And it can be quite quick if you're efficient with that method. Lastly, we've got example 3, which is asking us to factorise this. Now, there's a bit of a muck around here, so my recommendation would be just to think about completing the square for your factorising. But I'll show you some other alternatives. But let's start by completing the square. And so, sorry about that. If I was completing the square here, I'd write this down as z squared plus 8z. And then I'll just be clear that 8 divided by 2 and squared is plus 16. That gives me the perfect square. Then I get minus 16, which gives me the same equation. And then I get my plus 25 on the end. Now I can factorise this first bit. And that first bit gives me z plus 4 all squared. And then the second bit gives me plus 9. So I've partially factorised there. But I want to fully factorise this, and this is where it gets a little bit trickier to think about. But this is two squares now, but they're added together. I want the difference of two squares. So I'm going to change this to z plus 4 squared minus, and I'm going to write this down as minus 3 squared I squared. So I've changed it because I know the difference of two squared formula, but I don't know the sum of two squares. So all I've done is I've changed it to be a negative by incorporating that I squared component as well. Z plus 4 squared minus 3i squared. And now my difference of two squares says that this is z plus 4 minus 3i times by z plus 4 plus 3i. And the full expansion of that will take us back to what we had originally. So that's a really nice, clean method of completing the square. But there are alternate solutions. So one such alternate solution is the really old method of two numbers that add to give 8. and multiply to give 25 for our factorization. And the trick here comes from the fact that if they add to give a real number, then it must be 4 plus some number of I, because remember we've already recognized this one is a complex solution. So plus, let's say AI, and then 4 minus AI. It's the only way to make sure that when they sum them together we get a real number, and it has to be that 4 because we're going to end up with two things. And we get this. Those two numbers, 4 plus AI times by 4 minus AI is equal to 25. And then we just solve this equation. So when we solve it, we get 16. It's a difference of two squares. Minus a squared I squared equals 25. And that gives us negative a squared times negative 1 equals 25 minus 16. So that gives us a squared equals 3, which gives us a is equal to plus or minus, a squared equals 9, sorry. A is equal to plus or minus 3, which is good because we got the 4, which is what we had here, and we've got the plus or minus 3, which is what we've got here and here. So it's worked out well. And then the third option, which you'll probably like, it's probably the easiest option in the whole scheme of things, and that is to just write it down as an equation. It's really not the cleanest option, but it works. Write it down as an equation, solve that equation, so you'll come down here to z is equal to negative 4 plus 3i, or negative 4 minus 3i, and then put that into as a solution to factorize it. So say if they're the roots, we get z minus negative 4 plus 3i times by z minus negative 4 minus 3i. Expand and simplify, and you'll end up with that thing there. So that is the third option that you've got, but it really isn't as neat, so I'd be aiming for these ones here when you have to factorize. Now, the extension is, which we'll do in Unit 3, is to solve cubics, quartics, etc. using complex conjugates or with complex coefficients. And then we will do complex roots of unity in as well. But just note, everything you've now covered in this Unit 2 topic, minus this stuff here, makes up the entire Unit 3 topic. So you've already covered most of the Unit 3 topic, which is great stuff, and provides you some incentive to really get into it and make sure you know it. All the best.